Speak with you today. I am an MAUD second-year candidate. However, I'm one of the few that's actually doing a thesis that is outside of the urban design department, and Michael was kind enough to allow me to speak with you today. I'm actually looking at building technology, but I figured any opportunity to get in front of architects and planners, landscape architects, and just explore new technologies is definitely worthwhile. Just go ahead. So a lot of what I'm going to talk about today is going to be kind of like, maybe for somebody who's going to be like drinking from a fire hose, it's going to be very quick, but I promise when we get to the slideshow, we'll kind of step back and we'll go step by step. This is ultimately going to be a product design thesis, so we will just take it step by step. And I think what I'll do is to start off, we're going to just, I'll read the project's prompt. My background is in architecture and engineering. I came to the GSD as an urban design student, and I think during my time as an urban design student, it was amazing to look at large macro flows, systems design, a lot of what you've been seeing today. But for me, I started looking at seeing the toolkit for design as being flawed. So the actual physical items that we use every day in design of buildings, everything from, in my case, we're looking at HVAC ducting, to items that you may use in the urban landscape, such as bricks or blocks. Could these products be better? What would happen if you blurred the distinction between engineers and architects and started allowing designers to directly influence these types of markets? So I think what I'll do to start off is I'm going to read my project prompt, and like I said, I promise after I'm done, we'll go into the slideshow and we'll just take it step by step. Is this running? Can you hit play one time? Okay. So today, increasing concerns for building performance and environmental impacts have thrust substantial capital investment towards sustainable technologies markets. Accounting for nearly 20% of the domestic U.S. construction GDP, thermal ventilation devices most notably impact a structure's comfort, health, and energy expenditure. With many of the nation's largest products adopting criteria-based evaluation commissioning, such as LEED, Green Seal, and Energy Star, clients are increasingly expecting architects and engineers to not only deliver high-tech building solutions, but exceed the current horizons of modern performance technology. So, the DimpleDucks Research Initiative, which is loosely what I'm calling this so far, but it's actually looking at hidden infrastructures, is a research initiative that is dealing with the performative reevaluation of HVAC, heating, ventilating, and air conditioning, circulatory systems, and processes. For the past half-century, traditional square, oval, and spiral duct systems have become ubiquitous agents throughout the building industry. Efforts to address inefficiencies in blower operation and diffuser design have resulted in a myriad of high-tech solutions which focus on compensating for apparent lack of innovation or even complacency towards the ducts that unite them. The resulting innovation gap places extreme operational strain on ventilation conduits, which are commonly required to deliver air through complex structural passages and adopt a multiplicity of turns, kinks, and divergences. So now we get a little bit science. Akin to all viscous fluids, so you could take water traveling through your hose in your garden, air traveling through a pipe, or even oil pipelines crossing the Arctic. Any medium, when closed within a pipe, exerts frictional forces upon the walls of ducts which transport its medium. The resistant forces manifest as paralytic drag, which you might think of skin friction, so the air actually is sliding against the edge of the wall, and stack loss, which is if you think of a river, air and water sloshing down a pipe, bumping into one another. So when combined, it's estimated that the resulting net pressure drop as a result of these different frictional forces account for 6.7 billion kilowatt hours wasted every year in excess energy consumption in commercial buildings. And that's just the domestic consumption. 6.7 billion kilowatt hours would be the equivalent of I don't know, running the entire Los Angeles County for 7 days. That's how much energy we waste yearly, just in commercial buildings, not accounting for residential buildings every year. So it's quite a lot. It's actually becoming a more pervasive problem. And there's a few entities that regulate the performance of ducting, but they're few and far between, and there really is no set performance criteria based off it. So I think that's kind of good for now. Let me back into a slideshow for you guys, and we'll kind of take it step by step. Let's see here. So the initiative, or the idea of product development, really begins with identifying what I've been doing for the thesis is kind of splitting into two parts. A lot of this is market research to begin with. There just is no data associated with a lot of the building technologies we take for granted. Ductwork is one of them. There's no performance criteria for how it operates, and many of the manufacturers of spiral duct know nothing about, after they make it, it just goes out in the industry and becomes taken for granted. So the research, or the whole purpose for starting this was actually we had done a patent pending or an initial patent search on the processes, and I had mentioned before, the idea behind this whole process is the idea of using rhythmically textured surfaces inside ductwork. Rhythmically textured surfaces inside ductwork essentially create a series of small vortices, and you see these all the time. Think about golf balls. There's a lot of industries that utilize this technology outside of architecture and building technology. One is golf ball design, the idea of dealing with a boundary layer condition. Inside every duct has friction. Air kind of comes down the duct, bumps into the wall, mashes around, and you create a huge bottleneck. The idea behind rhythmically texturing the surfaces is you create a series of roller air bearings, essentially. You load the surface of that wall with little vortices, which ultimately allow air passing through the majority of the inner diameter to pass smoothly by and limit downstream turbulence. And so a lot of the work had been done initially with a concept analysis of trying to put forth a patent pending idea, which kind of summarizes the idea, but had not a lot of science behind it. And so the theory of taking this thesis beyond just concept became the idea of what the fall and what hopefully spring will result in. That's just the official document. So beginning the research process, the idea of looking at markets is when you're going to introduce a new building project or a new building product, you need to really source the needs of users. And that begins ultimately with owners of buildings, sourcing designers such as yourself, what are the needs that you might have of that product, and sourcing contractors who ultimately end up buying the product and installing it in the building. And so there's a whole list of different issues, one being cost, efficiency, long-run, short-term benefits, anywhere from designers which have many of the same concerns as their owners and their clients. Many of those people have the same concerns as their owners and clients, and ultimately we're looking at the guys who install it. Right now I'm in the process of soliciting 65 manufacturers of spiral duct and ducting products. I've looked at many construction firms and been soliciting their feedback on what they find lacking in the industry. And one of the major things that suppliers of spiral ducts say is that they're dying for people to innovate in this field. They feel like their products have become completely commoditized. One guy went so far as to say he feels like he's selling potatoes on the side of the road. He just sells the same product over and over again, and every time clients and every time architects call and look for performance criteria, he has nothing to say. He just says, you know what, it's ductwork, you figure it out. So he was very excited with the idea of trying to use design-related techniques that we use here at the GSD to reinvent these products. Life cycle design becomes a key component of looking at mechanical systems. I know it's hard to read here, but this is essentially the entire span of many of the products that we utilize in urban design, architecture, landscape architecture on a daily basis. Looking in particular at the light blue is mechanical systems, and so we're kind of spanning down from raw extraction, raw refinement, pre-processing, transportation, processing, all the way down to construction, ultimately use, and even at the very end of life possibilities. So the ability to maybe recycle a good and kind of get back some of that embodied energy. One of the things immediately that's grabbing notice is the fact that energy use for ductwork, the light blue here saying, is outrageously high. The second one there would be light loads inside the building, another huge inefficiency in most architecture. And then below, I'm just kind of starting to down. But below here, this is actually occupant loads, so maybe computer loads that are left on at night, and other such things. Also mapped on here are products such as fasteners. I believe we have finishing surfaces, and a collection of other like rain screen walls, anything on a building that requires a lot of embodied energy, many components, and it's hard to get rid of after its life cycle. This is the MEP market as it is today. It showcases mechanical, electrical, and plumbing units, but I've tried to break it down for you to kind of showcase what percentage of a building's budget in today's world is mechanical, and it's huge. 35, generally kind of coasting around 35% of any building that's being built today is being devoted to mechanical, electrical equipment. The smaller numbers are showing in particular HVAC, all the ductwork that goes into these buildings. We're seeing kind of US consumption here on the left and the rural consumption on the right. And what's interesting about these two is the United States is very mechanically intensive right now, upwards to 35%, but the rest of the world right now is catching up. And so a market for high-tech equipment is becoming more prevalent as very high-efficient mechanical units may cost a lot more. That cost benefit in the long run of energy savings is becoming more and more worth it. And so you're starting to see a lot of countries adopting maybe higher initial cost mechanical systems for that long range. This is just illustrating the intellectual property process. We kind of went through this at the beginning of, getting initial patent work and kind of following the government's proceedings of how do you develop patents, or how do you develop products, and how do you actually get them to a patent-ready state. So the idea, these are some conceptual renderings we've been working on. These are scaleless, but the idea of embossing dimples into traditional sheet metal ductwork. It has a twofold benefit. One, obviously, is the fact that we're kind of exploiting that similar boundary layer condition that you might find on golf balls or vortex generators on the wings of airplanes. The idea is that air is suctioned closer to the surface of that duct, and so you're effectively utilizing more cross diameter. And the second is the fact of embossing on the surface of the ductwork. I've talked to a few fabricators who have and do believe that this process would allow ducting traditionally made of 28 gauge steel or 26 gauge steel to be made of an even thinner gauge, because effectively by embossing it, you're increasing its cross-sectional diameter. So contractors are very interested in this. They can get their ductwork for 5-6 cents less per linear foot on a hospital or a large project. That could equate to millions and millions of dollars. And so these cost benefits have been fascinating through the process to kind of see how this would develop. These are looking at an individual dimple being kind of a combination of things. This is a compound, which is kind of you're looking at the inner surface of the duct, the dimple protruding outside, a combination of a vortex will generate in this hole, but also these little areas here called vortex generators come out, protrude into the oncoming flow and energize that, what is usually referred to as the boundary layer, which is a very slow-moving, sticky layer on the edge. And so looking at how ductwork goes today, these are some of the initial studies you saw earlier. Getting a base case reading, what's happening, what's out there in the industry today, and is it working or is it not working? So we're looking at square ducting, we're looking at round spiral duct, we're looking at round spiral duct with faceted corners, and anything you see in yellow is air that is not moving. It's air that's taking up space and costing owners and operators money every year. And you can get rid of that and make these systems more efficient. You're looking to introduce a product that might have a pretty big market. So just kind of continuing to see, you're starting to see that air peel off. You're getting an idea of how air is traveling through tubes, very rapid in the middle. As it makes a left-hand turn, very similar to how a race car might take a left-hand turn, it slams to the outside and blocks a lot of air. You end up getting these kind of vortices that formulate at the end. The idea behind my research is not only looking at the surface conditions of these ducts, which might come into play in reducing these areas. And this is anything in yellow is essentially a separation of flow. If you can limit that via surface condition, that's great. But also looking at maybe reevaluating the actual cross-sectional diameter of this. And so, like I said, we're very early on in this process. It's very intensive. There's not a lot of research being done on this. So everything that you're seeing is essentially, the forefront of knowledge. There's just nothing coming behind. A lot of what I found is looking at the automotive industry is doing a lot of work in this, aeronautics industry is doing a lot of work in this. And so as a proof of concept, these ideas work, and I'm hoping to integrate them into building technology and create products that really benefit the larger scale. So, thank you for kind of bearing with me. I know it's kind of crazy and nuts, but like I said, I'm working with John Stasi, who's here in our MDS program, and Martin Buckles, who's also in our MDS program. So I figured it'd be good to kind of get out from that environment and just kind of solicit information from you. I mean, a lot of you might have experience in building design, and I know any information from you or thoughts is always helpful in the process.
It seems to me like the way. I mean, have you done the cost analysis? I mean, where does this fall against the typical? Which the typical is really right.
The typical is really, yeah, I mean, these are all typical right now. These are typical configurations. And so you're absolutely right. I mean, the process of just adding another production step costs money, the embossing process. But then we start to talk about, like, there was kind of the rewards of, could you use a thinner material?
Yeah.
Would embossing this surface create more structural stability? And if it can, that offsetting cost might make it worth it. I mean, obviously, these are questions that we're looking for now. And in fact, this week, looking at getting manufacturers on board that can actually create the product. I have two right now that say that they're very confident that they can create the new system with the same cost structure. But that's kind of where we're at right now. Yeah.
How come, why are the renderings scaleless at the moment? Because it seems to me that scale...
It's very important. The scale is incredibly important. It all comes down to the viscosity of the fluid you're trying to transport. What's interesting about this is air. But what's interesting about this is it should work, quote unquote, that's what this is all about. It should work with a myriad of different fluids. And so the reason it's scaleless for right now is because depending on what type of fluid you're transmitting, it'll obviously have a larger effect on the size of this. And so this was essentially just a proof of concept that I was able to show manufacturers to see if they could go back to creating this. But you're absolutely right. When we go in, the scale of ductwork transporting conditioned air will be radically different than, say, conduit transporting oil or natural gas or any of the other materials that might benefit from a system like this.
Right, because, then in that case, then the idea, for patent purposes, right, the idea is like, then potentially meaningful for like a whole slew of different industries.
Like the good kids and the bad kids.
Well, no, that was a major point that I was thinking about. If you think about an urban scale, a much larger scale, I mean, think of the amount of infrastructure that we build yearly, right, that is transporting these mediums. I mean, it's in the streets, it's in our buildings, it's crisscrossing our countries, and a lot of its scale is dependent on what could be a lack of innovation. In fact, that we're transporting these materials that are incredibly, like oil, it's incredibly thick, incredibly turbulent, or
Yes.
water.
But at the same time, you start off with a specific argument about building scale and air circulation. And I think, yes, like I think the concept lends itself potentially to way more than that. But I want to perhaps push on this building scale issue a little bit because for those who have worked in architecture, we know, right? Like the size of ductwork is always a point of contention. Between the architect and the engineer and the owner and all this stuff. Right. And so then you're suggesting that, okay, I can make things more streamlined, make ductwork smaller, enable higher efficiency.
Which equates on that topic is if you have higher efficiency ductwork, the ducts can be smaller. And that's a huge. Okay.
So, yes, and then we would start, the typical architectural mind would start going there, but then also going on further. I know that ductwork is one of the dumbest things in the world, and it will keep on being dumb as long as the system itself is not changing.
Right.
And so you're focusing now on a particular point in a particular scale in that entire system. And in that case, I wanted why scale is important. It's not just because the ductwork can become smaller. It's because can I now imagine if this dimple is the size of something measured in nanometers versus something measured in millimeters, what kind of impact in my head that has on typical sheet metal? Because sheet metal is not going to go down to
nanometer.
Right.
It is millimeters.
There's also insulation on the inside that messes around with some of the things that you're talking about here. So there are a whole slew of questions that I would want to explore more. But then what about the system? How long are we going to be using ductwork?
Yeah. Well, that's okay. I mean, there are alternatives to ductwork. Cool beams are becoming popular. The problem is that a lot of these systems, that's why I'm focusing mainly on commercial buildings, because commercial buildings are utilizing cool beams. I have some experience using cool beams. They're just not effective enough yet to the point where they can actually condition, say, a hospital where you're dealing with negative and positive pressured rooms. They're not dealing at a scale that might be useful in commercial establishments. I think cool beams are an option that's interesting. I have all the faith in the world that they may become practical, but for now, ductwork is I don't see it going anywhere anytime soon. I think the idea behind it becoming smaller, more efficient is definitely where it's heading, but I don't see it disappearing anytime in the near future. But I think that because it's not disappearing, it's a good opportunity to now get in with it and fix this system that's quote unquote done.
The flip side of that question is like, there are others out there who are trying as hard as possible to like eliminate things like ductwork in their buildings, right? So things, even on a kind of like that level, like planets or region, I know that that solves some other problems, or like how does your work sync with people who are looking at passive strategies? And so there's this whole slew of questions that the product design is not linking in, and not to say that you have to do it, but
it's
back to your
And
comment.
also just to position it, it's really good feedback that what you're suggesting is a very short-term, efficient kind of lens through which to look at this larger issue. And as these other technologies develop over much longer timelines, yours is coming in sooner and quicker on the efficiency. And so if you can position the argument in that larger timeline, acknowledging the sort of future technologies in the future of building, then you can come into a very niche moment between these two ideas. And I would, like, as a designer in places, if you can maximize efficiency, give it a value, give it a size, give it a quantity. I mean, you already talked about scale and commercial building, then how much actual sheet metal is being saved from one particular example, like a generic example, and then link it to the land, like link it to actual resources.
Absolutely.
So that we can sort of visualize it.
Absolutely.
Can I ask a kind of dumb question?
Yeah, absolutely.
Which is, why would you do this project here as opposed to in the field? I mean, I'm asking that totally with wanting to know, because what is the advantage of doing it here?
The advantage of doing it here that's unique is the fact that we have access. What I've been plugging into is the Harvard Innovation Lab, which has been a really interesting, and MIT being next door, it struck me as a very appropriate time to look at an idea that might ultimately fit. I mean, this is one of those theses, I think, that will, ultimately it would be great to have prototypes, working prototypes at the end, an actual product. But I'm approaching it from a standpoint that says, look, we're going to work on this, and if it fails, then you know what? It was an interesting learning process. There's nothing taking away from the process of creating a product, but at the end of the day, with the Harvard Innovation Lab, with MIT, and a lot of the people in this building, in the MDS program, even in the urban design program, looking at research and extraction, it seems like a very appropriate time and place to test ideas that are out of left field, but that might be developed further into something that could be.
Yeah, they're not out of left field. I don't think it's just the context that is a surprise. But highlighting that, what you do very articulately with the confidence it is. Knowing not enough about this, just great. But what I'm trying to say is, can you make light of that? In other words, how would you be as innovative about going to market with something like this, for instance, or reaching out to innovative strategies for not just going to the bad guys or whatever it is, and actually reaching an audience that you're more engaged with anyways by doing it here.
Right.
Sort of, how can you non-commercialize it? Right?
Yeah, no, that's a very good question. And what's interesting as well about this process is that's what I'm discovering now. Like I said, there was nowhere to start. There really wasn't a starting point. There was no research that had been done on this in the building technology field. And so these are the questions that I wanted to bring up today, because that will very well shape the direction that I take the project. And if we're talking about an audience, like the bad guys, the bad guys, they're bad because they're destroying the landscape with all of this infrastructure. But if there's a way to mitigate that for the better, that might be something to look at. But also, if we're looking about passive strategies, I think a lot of the passive strategies, cool towers, the circulation of air isn't going, any fluid, it's not going anywhere. We're always going to transport mediums, whether it's, passively or actively. But this is the type of technology that can work, I think, at all of those.
I just want to interrupt you for a minute. Sorry. I think maybe where Lisa's question is coming from a little bit, and I have some of the same feeling, is I don't doubt this possibility at all, but I guess I want it to be a little less of a kind of inevitability and more of an exploration. And I think I don't mean this at all disparagingly, but it comes up a little as a TED Talk, and it doesn't need to be a TED Talk. Like it should be a little more academic in the way that you're presenting it. And I think part of it, actually a very simple thing is, I presume there are other alternatives other than dimples that might, kind of reach, and you're saying, this is a product, it might fail, but actually the role of a thesis is actually not to nail your answer on the first try, but to work out some of those failures before you sort of get to market, whether it's in designing a house for a writer in the mountains or designing ductwork. And so I almost want, this is like a comment that I probably will say more than once, but I want a little more poetry in this.
Sure.
Like loosen it up just a little bit and let a little more kind of other options in.
Well, I think a lot of I'm hoping, like you mentioned, the thesis. A lot of the images I showed you, that was done early just to kind of showcase. But I think the thesis will ultimately be about optimization. And what optimization means is testing. Like you said, does it have to be dimples? Well, no. What's the shape? What's the arrangement? How are they derived? I think the thesis will take that track and be very exploratory in being poetic and saying, is there any market aesthetic that might be created by computational designing it this way? What's the benefit of its performance that looks like this? There's trade-offs, and I think a lot of that will be derived by, quote-unquote, creating an optimization thesis
Well,
that has.
how about it's just much more straightforward? You've done all the sort of quantitative work. Maybe going to Brian's, it's a little bit tongue-in-cheek maybe, but maybe you try it at just two different scales, maybe, and because you're the GSD and you're MAUT, you try it at some sort of urban scale, and then you try it at an architectural scale. What are the I'm just curious what the possible implications are, and it could, really get to the point where you understand just dimensionally, not in a very abstract way, but like a truly human way. What are the implications for the people who are finally going to design around it, live in it, that kind of stuff. And I think it might actually cause you to realize that it's not a perfect solution.
Sure.
That also makes it a little more of an urban design thesis, which, none of us are your advisors, so you have been told this is kind of totally fine, but instead of just having a kind of prototype at the end, you'll start to articulate some of the more larger kind of...
Ramifications.
Yeah, and that's interesting. This is interesting because it's actually potentially redesigning the most sort of ubiquitous of architectural elements, and so presumably it will have some other impact. And, I don't want to change a brief, but maybe you do need to kind of examine those sort of broader implications a little bit, at least as a thesis. That doesn't mean when you leave here you can't, sort of market it as a product, but I think it has to be more than that as a thesis.
Well, ideally, it then becomes part of your TED Talk. You realize the aspects of this at various scales that really help to either sell the project or just fine tune the pitch. In a way that people can really grasp it compared to their own lived experience. And I think
I was thinking just one thing is sure. I really believe this is, if I believe you, that this is going to be something revolutionary. So I was thinking about what kind of obstacles you can find in this way of making it real. So usually what happens is technology into building is absolutely regulated. So usually what happens is innovations are always facing standards and regulations. So if you have to change standards or regulations to introduce this technology, this is something like David and Goliath. Yeah. So this is something you have to have in mind from the very beginning. So that's the real world working. Here we are here in our lab, and if we want to live with the reality, you have to know how it works. And you have to be facing these processes that maybe are not the most efficient one, but they are there, and changing them is absolutely amazing effort. So this is, I think it should be, if you are in a way trying to live with reality, you have to pay attention to it also.
Absolutely. I think that's a super interesting point, because when you're talking about reality, the frictions in the political human life of getting stuff built, not just the friction within the
I mean,
itself.
it happens always happens that in construction, you try to include like new technologies. Like regulation are so inefficient usually because it's like there's a minimum standard that you have because it's like also a matter of safety. And when you deal with safety, it's like everything is like increasing everything, amount of material, everything.
Yeah, I mean, that is definitely a great point. I had thought about that. I mean, that speaks to the real world friction, not the friction of the pipe, the friction of people adopting any technology. It's difficult to convince people that are used to doing something one way to maybe do it another way. And so I have thought about that, the ability to be used with existing systems, the ability to be installed exactly the same way. I mean, I keep telling people I'm not trying to reinvent the wheel of how these systems are regulated, on how they're installed, and I'm trying to definitely stay within that framework because that framework, you know, whether it's safety regulations, OSHA, it's ASHRAE, or any of the other sheet metal performance criteria, like you have to maintain those standards. It's important so when you're innovating and thinking about a new product.
Well, but you don't have to maintain the standards. I mean, I think you push against the standards, and like this is the perfect place to be to question whether ASHRAE, I mean, maybe the ASHRAE standards are there because it was driven by the technology, right? So, which you're suggesting changes. So,
yeah, it's a push and pull. I mean, on a performance standpoint, absolutely. I'd love to rewrite the rules.
We have to
No
move on.
problem.
Thank you so much.
Thank you very much.